Okay, thank you for the introduction. It's a pleasure to be here, and I will talk to you about how we are combining an unsampling method with machine learning, and I think this is just the beginning of what promises to be a very fruitful direction. So, as was said, since the very beginning, when I went to visit Raman in 1980, I fell in love with this technique. As I became a practitioner of it, it became more and more clear that there were lots of improvement to be made to make this kind of simulation even have an impact even larger than what already had at the time. And there are several directions in which one can think of improving simulations, accuracy, time, complexity of the system, and I think I value for extremely important the issue of understanding. This should be meant to be a fourth axis, and that it should always guide what we do. It should be what we get at the end of our simulation. Okay, so I will address a couple of these two things, especially time and accuracy. And rather than doing it in abstract, I will focus on a particular application which illustrates a combination of two issues and how we went about solving it. Suppose you want to study silicon. Silicon, of course, is the most important element. But from the chemical physical point of view, it has a peculiar behavior because at low temperature is the prototypical semiconductor, but when you bring it to the melting temperature, the melting is accompanied by a metal-non-metal transition. So during this transition, there is a massive change in the chemistry of the problem from semiconductor to metallic. And there are two difficulties in this respect. One, the fact that melting takes place, or freezing, as you wish, takes place on a time scale which is really macroscopic, as our daily experience, say, with the freezing ice demonstrate. And the other thing was I dealt with in some detail is the issue of finding a potential which is able to describe both sides of this problem. And of course, one could try to do ab initio simulation, but the time scale for this to be possible are too long, so one has to find a different approach, and we show you how we combine these two things. Okay, so let's go with the well-known time-scale problem. So the phenomena that surround us, they occur on a time scale which spans orders and orders of magnitude. And the issue with molecular dynamics is that the integration time step is very small because it has to do with the fastest vibration in the system. And to bridge the gap from here and study going to milliseconds, second, and beyond, it is not possible by mere computational power. So something must be done. But before discussing what we do, let's go at the root of the problem. Why are there these time-scale problems? That's related, for instance, to the fact that if you study a chemical reaction, so the folding of a protein, or the crystallization, or whatever, many phenomena in physics and chemistry, you're confronted with these two well situations. So you have one metastable state here, another metastable state there, and there is a big barrier to go from one metastable to the other. So if the time it takes to escape the well is of the order of the barrier, and which can be many times KBT, that's an organic chemical reaction time scale. So you see, this can be days. And in fact, our colleagues in the lab, the chemists, they cook their things for a very long time, and that's why. So it is not conceivable that we wait, we simulate such a long time. And what happens here, why there is this larger thing, is that thing fluctuates in the bottom of the well, and occasionally there is a rare but a crucial fluctuation that takes you over the barrier, and so the system discovers that there is the life behind the mountains, and they go and explore the other valley. Okay. So rare events are driven by infrequent fluctuations. So we want to have a language for describing these generic situations, and I'll make an example, because the usual approach would be to use the potential energy surface to look for transition state, and the potential energy surface of system or condensed matter, they are so complicated that that's really not possible. And so we want to sort of find a language to describe this phenomena in complex situations, and then find ways of addressing the rare event. So let's think, for instance, just to give you an idea what I later mean, a situation in which I have a crystallization phenomenon. So I start from the liquid, and I cool it, so the minimum of the solid is lower in energy, and so eventually the guy will go from here to there. How it goes, there are fluctuations. At a certain point, a cluster of size n of the new phase being formed, and the formation of a cluster of size n has a free energy cost, is a favorable contribution due to the fact that this second state is lower in energy, but you have to pay the price of the formation of an interface between the solid crystallite and liquid, and this leads to this thing. So these are well-known elementary considerations, but let's abstract from it and make a generalization of these things. Consider what steps, a conceptual step we have done here. Okay, so we have taken a system which has a complicated potential energy surface. We are ignoring the potential energy surface. We describe a 3n system by one parameter, the cluster size, and we talk about the free energy and not about energy. So this is the framework in which we're going to do, and our system will be described in terms of the parameter, we call it collective variable, and the free energy surface. And we make this simple sample general. So we introduce a set of collective variables that are supposed to describe the system, that are difficult to sample, and we marginalize the probability distribution to get the distribution of our collective variable, and the free energy is nothing there. So this will be our language. So as I was underlying, this amounts to a dimensional reduction. We go from a high dimensional, a rugged potential energy surface, to low dimensional and smooth free energy surface. And also we have a nice way of interpreting our result, because if this order parameter, for instance, allow us to distinguish between solid and liquid-like particle, and you see this mess actually corresponds to a situation in which I have a slab in equilibrium with it. So there are many advantages of doing that. So we are left with the issue now, because we haven't done anything to the system, of sampling. So we start with minimum A, and we want to go to B. And the system spontaneous is not going to do that. So we follow in the footstep of a very old paper, by Torri and Vallot when they introduced umbrella sampling. In that paper, there is already the concept of collective variable. And so what they do, they add to the original potential an extra bit, which is called bias, which is function of the collective variable. Of course, in so doing, we change the dynamics, the probability distribution, and so on. And so we need, at the end, from the bias run, to go back to the unbiased average, and this is done through this simple reweighting formula. It's called umbrella sampling reweighting. Okay. Okay, so now the next step is to construct this bias. We have devised two methods in the last decades or so. One is called metadynamics, and the other, we call it variational sampling. Metadynamics is rather simple in conceptual and its implementations. So you have again a two-well system, and if we don't do anything, the barrier is very high, and this guy will fluctuate all the time in the minimum and never protect. So we'll give a helping hand, and the helping hand comes in the shape of adding, as we go along, a repulsive Gaussian. So wherever I go, I deposit it. So it amounts, in a certain sense, of filling the well and making the landscape smoother, rather than being rugged. So this is the basic, and there are two variants. So there's the initial variant, which we developed with Lyo, and there is what we call well-tempered metadynamics, which is a later thing. I presented this metadynamics in a rather hand-waving form, but there are rigorous results which are based on the theory of stochastic iterations, and so the stochastic iteration implicit in the metadynamics eventually can be described by this equation, and the solution of this equation is such that the metadynamics can be looked at as a way of filling the well, but also as a way of enhancing the fluctuation. So if you do metadynamics, this would be the distribution of your collective variable in the unbiased ensemble, and this is what you get in the metadynamics run, and gamma is a parameter that you can choose. What is the effect of this transformation? So originally, you were sampling the red ensemble. So you have two states separated. Now you do metadynamics, you sample the blue ensemble. Now the gap has disappeared. The peaks have become broader, and the rare events, which are all important in life, like when you meet the woman of your life, that's a rare event, but it's very important. You can explore the Taylor distribution of very nice things or different things happens. Okay, and all these things is rigorous. Okay, so that's one thing. So this is the method. Now let's go back to silicon. In silicon, we need, if we want to study, we know how to do this rare event, study the crystallization, but we need still to build the potential. And so we can't do DFT, so we use neural network we train a neural network such that from a series of accurate or relatively accurate DFT calculation, we can extract a potential. And as was mentioned by was mentioned by Giuseppe, first thing was done in the dark ages, before the recent flare activity. But there are essentially two ways of going about it. One is the neural network, and the other is based on Gaussian processes. Okay, so if you need a neural network, you have to be careful because you want to reflect the physics of the problem. And so what we do, this E1 is the energy of particle 1, E2, energy of particle 2, and so on and so forth. And all these neural networks are all equal. So the same neural network, each one describes the potential of each particle. So in this way, the permutational invariance is automatically satisfied. The other care that you have to take is that you want your potential to be translational invariant and rotational invariant, and so you don't feed into the neural network directly the position of the atom, but certain symmetrized combinations. And there are different ways of going about it. Now, there's a nice way done in Princeton by the joint effort of Roberto Carr and Wayne, and we use this variant in what follows. So you take a set of configurations, you fit this neural network, train as the people in this, and you can fit the potential, you can fit the forces, the virial, whatever. So now the issue is how you choose the training set. And that's what we have done recently with Luigi Bonatti, who is in the audience, identify a way of choosing an appropriate training set, because this is a transition between two states. There are solid state and liquid. If I train only on the solid, I cannot do the liquid. If I train on the liquid, I cannot do the solid. So we have to select. We can do this randomly, but we prefer to follow a different pathway. And so what we did, we started with the classical potential, which is the famous Sillinger-Weber potential. We choose appropriate CVs, which I did not discuss it, and we made a metadynamic simulation. And you see that this goes up and down from liquid to solid many, many times. Here we see the power of metadynamics. This would be the peak. There is a scale issue here, but to make the picture visible, this is the peak of the liquid. This is the peak of the solid. If you do metadynamics, we broaden these things, and so we get a whole range of configurations. And especially those very important configurations in which you have a coexistence between solid and liquid. So we have the finite side, we have the interface, and so on. And so we take a sequence of configuration thus generated, and we train our network there, and we find a potential, and there's the inevitable movie where you can see out of the liquid appears, with the help of metadynamics, a silicon crystal. Okay. And we can go on. And then we can see, we can calculate the free energy as a function of temperature. And you see as function of temperature the relative depth of the two changes. And from this, you can calculate the free energy difference and the melting point. Okay, so you can amuse yourself to see how the crystal light grow, and you see that it's some of the larger cluster already look like crystallites. They form nice facet. So it's a bit different from the standard, the round picture of the nuclei. Okay, so let's move on, and of course, you need to do this calculation. You need to identify collective variables, and this has been around doing many things here. But today, I will talk about what I call physics-informed machine learning methods. And again, I like to start with examples. And let's look at this very simple S-type 2 reaction. There is a chemist called, so I have a chlorine, comes here, and this chlorine is expelled. Let's suppose the two chlorine have a different isotope, and so we can distinguish them. And so the way the reaction occurs, this is the distance d1, this comes here, and the other is expelled. So there are these two, we call descriptors, that identify essentially the reaction. And so what we can do is to make two separate calculations. One in state A, and look at the fluctuations of the position of the system in the space spanned by D1 and D2. So this would correspond to state A, say, and this would correspond to state B. So these are roughly Gaussian things, which I can characterize by the average value and the fluctuation matrix. Okay, so what we want to do now, and these are two states which are very well separated in the 3n dimensional space. To get the CV, we want to project these two states into, say, one-dimensional thing. So it's a problem of classification from the point of view of machine learning. And so how we go about? So we want to classify the state on the basis of this information. This information doesn't require, actually, observing the transition. So we went to the literature, and being simple guys, we tried to the simplest classification method, which is very old, and it's called the linear discriminant analysis. And so you try to find the direction in which, if you project your data, they are maximally separated. And in linear discriminant analysis, this is obtained. So this is a linear equation in the space of the descriptors. I find that the orientation of this curve is obtained by minimizing this ratio. Upstairs, there is the distance between the center of the two projections, and downstairs, there is a measure of the width, the combined width of the two, which in linear discriminant analysis was taken to be the sum of the two distributions. Okay, you can do that. You can do for the S2 reaction, and it works nicely. But if you do systems which are more complicated, it's not such a good idea to use this thing. And we trace this to the fact that in this description there is no information about the relative position of the two wells. So this in this case is symmetric, but take a generic case. They could be very different. So you want to feed in your discriminant analysis some information about the relative weight. But we don't know what the weight is the purpose of our things. But there is a generic thing. So if you have a state which is very tightly bound, its fluctuations which will be very small. And this is likely to be lower in energy than a state which is very diffuse. So how do we go about this thing? So in the theory, we substitute to the sum the so-called harmonic mean. So we take the inverse of the average of the inverse. In such a way, we give more weight to the state which is closer, tighter. And this is really, it's amazing how well it works. It's really embarrassing. Very simple thing. And I think there is some message here, in the sense that it's all well and good to use machine learning technique, but it's even better if you add a pinch of physics to it, and you can get much more out of this method. Okay, so I will not. one thing that I found always amazing, suppose you take this other reaction, huh? And that's a double bond, single bond, double bond. Comes at this molecule. When they are together, the bonds are changed, the pattern, this becomes double, single, 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 single. Now, even before, and you look at our CV, for instance, in going from here, this is a double, becomes single. So double is shorter, and this is larger. So that's what happens. If you D2 is the other way around, and so on and so forth. If you look at this number, you can see the chemistry of the problem being described already at the level of determining the CV, which again amazing. So you can study chemistry, so without knowing the transition state, without knowing the reaction path, all the properties of the system are encoded in the fluctuations of the two states. Okay, and you can calculate free energy. So this, I don't think there are many chemists here, so I will skip this, and I just say that I showed a simple example, but you can have also a series of biological applications. I will not go into the details of it, but this is the interaction between a ligand and this big protein in a membrane. You can do this. You use just what we said, and you can calculate how this ligand goes out and so on and so forth. So that's just to say that we don't do only simple systems. Okay, the last part of my talk will be with the even more recent development, which is based on what we call variational enhancement. So with Omar Balson, when he was in my group, we realized that there is a way different from what I've described earlier on to determine the bias, and it's based on the variational principle. And so we wrote down this functional of the bias as my collective variable. So I have this term here. This is my arbitrary distribution, which we call PS. It's a target function. I can decide what it is. It's flat, it's hilly, it's whatever I want. It depends on what kind of calculation I can do. If I minimize this functional relative to VOS, I find this relation, so I can reconstruct the free energy surface. So it's a way of getting the bias. And at the minimum, what happens, the distribution here in this thing, which is the distribution in the bias ensemble, is equal to my target. So by minimizing that, you make the bias distribution equal to the target. It will not be a surprise to you that having this property, the omega, is very close. So it's very close. It can be expressed, in fact, to as a Kullback library divergence, in which you measure the divergence between PV and PS. I prefer to write it this way because in my eyes, it's more transparent. For instance, this term is the reversible work that you do on the system by taking the bias of, going from zero. And this is kind of Lagrange series or Lagrange multiplier that control the bias. So that's way. I could have written a Kullback library divergence, but I like this better. Okay. Okay, so how do we go about minimizing this functional? There are different ways, but the simplest is that I expand my bias into a basis set, like you do in quantum chemistry. Now your variational parameters are the coefficient of the expansion, and your functional becomes a function, and we need to minimize that, okay? And we use the stochastic steepest descent algorithm, and the force that drives the gradient has this shape. Is the derivative of the bias relative to the variational parameter. This is calculated in the bias ensemble, and this is calculated in the target distribution. And so what we did, we did something that's not normally done in neural network of machine learning. We use a method due to these two gentlemen, in which you introduce the average value of the parameter. So you see you average over the past, because this alpha will be fluctuating. And then we expand the force to linear terms in the difference between the average and the instantaneous value of the parameter. And this worked very nicely. I mean, we had nothing to say for this kind of things. Then we decided, okay, so that shows how it goes. So we do the average. Okay. We decided, okay, so now, yeah, there are some issues when you do this way. You have to decide what your basis function is, which is can be a problem. Or very often you do on the basis of computational convenience rather than physical understanding of really what happens. If you have sharp features in your free energy surface, you have to include a very large number of coefficients in your expansion. If you have a multidimensional thing, the number of parameters just blows up. So we decided, okay, so why don't we try and use a neural network to express the bias. And so we construct a neural network. In this case, it's just two CV that enters, but you can have as many as you like. Or, I mean, not as many as you like. We can have several, and then we have this kind of triangular things which ends up into the bias. And so in the language of a neural network, our functional becomes the loss function. And we try to do the Bach and Moulin, and eventually converge, but was so painfully slow. So, and so we had to adapt the strategy to find the things. So I started with a simple example. This is a two-dimensional potential. There's one minimum here, one minimum there, and of course a convenient CV would be one that goes in this direction, because that's where the bottleneck is. But suppose that I'm stupid, or I don't know, and I choose the X as CV. And so, which is actually, it's more representative of a real-life situation where it's very hard to find the CV, but you find a reasonable approximation to the CV. So we use Adam stochastic optimizer, and then, so you see, it's the first part of the run. It goes up and down a lot. Then we monitor the convergence by running estimator of the Kullback-Leibler divergence between the target and the bias POS. When it goes below a certain threshold value, you see here, we start diminishing in an exponential way the learning rate. I call it delta t, but I mean, in this context, it's called the learning rate, and we bring it to zero, or practically to zero. From there on, we don't touch it any longer, okay? And that's the result that we find. If we stop here, the bias that we find is this green curve. The exact one is the red. So we get close, but not quite close. But that's not so important. I mean, also in neural network literature, you really don't go for the minimum. Typically, you go close to the minimum so as to have a useful approximation or a useful description. And this is the same that we do. So we take the value in this stage, the potential doesn't change any longer, and we use the reweighting things that, so this is a static potential, and we can calculate, and you see, if I do that, the gauss converges very beautifully, and now I don't think you can see, but the red curve contains the exact result and the result of the reweighting. And so that's what we have to do to have, okay. So I show a couple of examples. This illustrates better in this field, like the hydrogen atom of a rare event is the study of these two little proteins, which is flexible, described by the ideal angle, phi psi, and it has free energy surface, which has two minima, really, correspond to different conformations. Now, if we do the same thing, we stop when, according to the recipe that we use in general, there's one recipe for everything, and that's what we find. Now, if we do reweight, we got this. If we got the perfect thing, we got that. So already, that's pretty good. Huh? You do a little bit of reweighting, and all the fine details come to life. Okay, so then again, silicon crystallization, that's how it looks. Here expressed a fraction of cubic diamond atoms in the thing. We find the barrier, liquid, solid, again reweight and deep. And the original thing, they are not very different. But if you want to really be precise, you do the reweighting. Okay, so I have to thank people on my group, and in particular for the subject of this talk, I would like to acknowledge Luigi, who has been with our neural network guru, and we have done the silicon crystallization and the last calculation together with, I forgot to mention UAE here, and the variant of the linear discriminant analysis has been developed together with Giovanni and Dan Mendels, who is now in Chicago. And that's the end of my talk, and ready for your questions.